Time to do some calculus problems. How about section 2.6? I don't like that pen. Let's try this one. Section 2.6. Oh, that's better. Numbers 18 to 40. The evens. I think you've already done the odds. All right, so we've got some limits here. Let's see what we're looking at. In 18, I have the limit as x approaches positive infinity, the sine of pi x over 2 minus 3x. All right, now in a situation like this, this is kind of like a composite function, which just means that it's got like an inside, and then there's another function that's operating on that inside. So before I can think about what's the sine of whatever, I think I need to focus on just what's the inside part here. I'm always going to approach these that way, try to deal with the inside first. So what's happening as x approaches positive infinity, what's happening to this? Well, this is just like a highest power top and bottom. I've got x to the first here, x to the first here. Highest power top and bottom, it's a tie, so it's just the ratio of the coefficients. That's pi over negative 3. So the limit as x approaches infinity of this is just that. And now I'm just looking at what's the sine of negative pi over 3. So sine of negative pi over 3, I'll give you a second to think about that in case you're just catching up to where this is at. That's negative square root of 3 over 2. All right. And this is, by the way, I should just say about that one, this is the way that trig happens in calculus class. It's not like you're going to have a very special quiz, like just on unit circle stuff, and then it's all done. Just you're doing calculus, and all of a sudden you need to know some trig. So it's going to be there all the time. You've got to know it, know how to do it. All right, how about number 20? Got the limit as x approaches positive infinity, natural log of x plus 1 over x. So real similar to the last one. As x approaches infinity, here I've got highest power, top and bottom. It's a tie. So ratio of the coefficients, 1 over 1. Natural log of 1 is 0. Same kind of deal with trig functions. You just got to know about logarithms. It happens. Then we got one of these. Limit as h approaches 0 of sine h over 2h. So let me think. I'm trying to remember where you guys are at and what you know about limits of trig functions. So in your notes for this section, one of the things that we got is the limit as x approaches 0 of sine x. This is the thing you got from that little squeeze theorem proof, which you don't need to know how to reproduce that. You just need to know that this is the punchline. So we got these two things here. And because this is equal to 0, it doesn't matter what order those show up in. It could be cosine x minus 1. That would still be 0, because negative 0 is equal to 0. And another thing that's really, really helpful to know about this one is you can set up this chain here. Like I could do with this one, I could say, well, look, if I could get these things to match up, then I know it's equal to 1. But here there's an h and there's a 2h. So what do you do with that? Well, you just say that's the same as the limit as h approaches 0 of sine h over h, and then I'll just take the 2 and pull it off to the side here, right? That's totally legit because 2 times h is still 2h. And then this is 1 times 1/2 is 1/2. So that's fine, but after you've done a few of these, what I'd like you to see excuse me, is that if you have any combination of sine functions, tangent functions, and just regular old linear functions, then let me show you what I mean. If you've got the limit as, I'm going to say x here, approaches 0, of sine of ax, in other words, there could be a number here, sine of ax, or tangent of ax, or just regular ax. So any one of those over the sine of some other number, bx, or tangent of bx, or just bx. Of course, if it's just ax over bx, that's like highest power, top and bottom. It's just a over b. But all of these, any combination of those, the limit's just a over b. I'm not sure if I said that exactly in the notes, but 'tis true, and I'd like you to be able to recognize that, and if you do recognize it as that, then I don't really think you need to do any work. Like if you see a problem like this, you're just like, oh, it's one of these ones, sine over h to the first, so it's just 1/2. And if you do that, I mean, you can play around with these and convince yourself that it's going to work. Why do the tangent functions also work? The tangent functions also work because tangent is sine over cosine, and the cosine part of it, as x or h or whatever approaches 0, the cosine part's just going to be equal to 1. So that doesn't change anything. All right, so let's use that as much as we can. Also, I don't remember, maybe this is the evens, so maybe I did this exact same thing in the odds video, which I made a while ago. I'm making a lot of videos these days, so a little hard to keep track, know what I'm saying? So here, there's a sine squared theta over theta. So I'm going to take that sine squared and break it up into those two. So what's happening here? Well, that's just an example of this thing. That's 1 times, and then this is 0, so 1 times 0, that's 0. So that extra sine function on the top knocked it down to 0. 26. Can I just write down 6/8? Come on. We just did this whole thing just so I could do that, because it's an example of this. 28. I'm going to write this down, but I'm going to do a little bit of surgery here. I'm going to split up the sine squared into sine x times sine x, because that's what it means. And then I've got 3x squared. So how about if I put a 3x here and an x here? So sine x over 3x, that's one of these, right? That option. And so that's 1/3, and then this is just 1. So that's that. 30. This might be getting a little trickier here. So I've got when you see something like this, there's a couple things before you try something or give up or whatever. Think about what are the options here. There are a couple options. You might be thinking about these things and wondering if that could take us somewhere productive. So we could try that. Let's try, go ahead. What if we multiplied by h over h, which is legit, right? And then I broke it up with the goal, I'm trying to get it to match up to these things, which I know about. So sine h over h times, and then here, h over 1 minus cosine h. So what does that do for us? Does that do anything for us? I have here, this goes to 1, and then here, what about this? Well, it's this thing, but it's upside down. So what happens, I hope that at this point, you guys have a little bit of an intuition, or maybe a lot bit of an intuition, that when you flip 0 over, if something's getting closer and closer to 0, well, if that thing is on the bottom, or in other words, if it's upside down, then that will be getting closer and closer to infinity. So this, if 1 minus cosine x over x goes to 0, then that same thing, h over 1 minus cosine h upside down, is going to go to infinity. So 1 times infinity does not exist. All right, that was a little trickier. Let's see what we got in 32. The limit as x approaches 0, x over cosine of 1/2 pi minus x. Let's see, that's interesting. So, oh yeah, I think I see this is tricky. So, as x approaches 0, let's just see what's happening here. If I plug 0 in here, then that's just going to be cosine of pi over 2, but cosine of pi over 2 is 0, and so that might make you think, wait a minute, if the cosine of that, then this is like a little shift of this function. This basically shifts this. Let me do a little bit of sketching for you. So here's the cosine function. Right, it looks like this, and does its little dance between 1 and -1 forever. So what happens if you do the cosine of that? Like, what does this look like as a function? The answer is it looks a lot like a sine function. And how are you supposed to know that? Well, there's a couple different things that you can do that you can know about this. First of all, cosine is an even function, which means that if you have the cosine of x and you have the cosine of -x, well, look at the cosine function. What happens if you plug in some value x over here? And you get some number. What happens if you plug in the exact opposite of that number? You get the same thing. It's a mirror image of itself. So if you plug in a positive, negative version of the same number, you get the same thing. So that means that I could flip the sign of what's in here. That's the same as cosine of x minus pi over 2. And x minus pi over 2, if you put in here a minus pi over 2 inside a function, you know what that does. You've done this in pre-calculus class. That shifts a function to the right by this much. So if I shift this function to the right by pi over 2, that makes it over to here. And guess what that is? That's a sine function. So this is equal to the sine function, and then limit as x approaches 0, x over sine x. That's this upside down. You know what 1's equal to when you flip it upside down? Right. That's tricky. If you want to know, like on a difficulty level, 1 to 10, for the kinds of problems that you should expect to see on the Chapter 2 test, that's pretty hard. I'd give that one like a 9. Because there's a lot. You got to dig deep into that. So that, if that showed up on your test, I'm just trying to make you feel at ease a little bit here. If that showed up on your test, it would be, if not the hardest problem, it would be one of the harder ones, hardest ones, let's say. And speaking of hard limit problems with trig in them, here's another one. So what are we going to do with this? So same deal. If this showed up, this would be the hardest problem on the test, I think. Okay, so anytime that you see cosine squareds or sine squareds in a 1, you got to think that there might be some sine squared plus cosine squared equals 1 going on, right? So cosine squared minus 1, that'd be like moving this over here So if sine squared plus cosine squared equals 1, then cosine squared minus 1 is equal to negative sine squared. That's how things would shake out if you want it to look like that. So I could do that, and anytime you see this 1 minus cosine thing, one of the options that you have is you could multiply by this thing, kind of looks like the conjugate of something, right? Instead of 1 minus, you multiply by 1 plus the same thing, and it does that difference of squares thing that you know about from various algebra classes that you took once upon a time. So that's what I'm going to do here. I'm going to rewrite it now. Here on the top, I'm going to end up with 1 minus cosine squared 3h. And then on the bottom here, this is equal to that, minus sine squared 5h. And then here I just have this thing. This one multiplied in here to do that, but this one's still just hanging around. Right? Okay, now what? So now, why did we do this? Because 1 minus cosine squared, this is equal to sine squared. So that's the limit, h approaches 0, of sine squared 3h over minus sine squared 5h times 1 over 1 plus cosine 3h. Okay, so this right here, I need to just split this up into sine times sine and sine times sine on the bottom. So then it's just examples of this thing again. I have the limit as h approaches 0 of sine 3h times sine 3h there's a negative sign there, only one negative sign, right? And oh, I bet Mr. Kraft's going to come on and start talking here in a second. Hold on one sec, I'll be right back. I'm going to take my phone off. So you can try to finish that problem there and see what's going to happen. And coming back. So here, this is equal to 3/5 with the negative sign. This is another 3/5. And this is 1 over, as h approaches 0, cosine of 3 times 0 cosine of 0 is 1. So 1 plus 1 is 2, so that's a 1/2. So negative 9 over 5 times 5 is 25 times 2 is 50. That's a doozy, that one there. All right, let's see. We're almost there. Number 36, the limit as x approaches 0 of x squared minus 3 sine x over x. Well, when you're just dividing by an x like that, you can split that up. This is my first instinct here. Say that's x squared over x minus 3 sine x over x. Right? Usually we're used to taking, probably more of our algebra training involves taking things like this, like getting the common denominator and trying to put them together like this. But that's a two-way street, right? You can undo that. So x squared over x, that's just 0, right? I mean, that's, well, this is equal to x, and as x approaches 0, that's equal to 0. And then I just have minus 3 sine x over x, that's just minus 3 because this is going to go to 1 So that's all. That's pretty easy after that last one. But, you know, it's hard to see when you look at one of these problems. It's hard to know exactly what direction it's going to go in. You've got to leave yourself open to the possibilities. I'm going to go ahead and write this one. Same deal with the sort of uncommoning the denominator. I think I just made that up. But it's a decent way to describe what's going on here. So this turns into tangent 3x squared. You got to look at where these squareds are. That's really important. This is just the tangent of 3x squared, and there's only one of them, x, and then there's an extra x on the bottom. There. Plus. Oh, wait a minute. No, I don't want to do that. And this is the sine of 5x. This means sine squared means I've got two of those. All right, so this one is those things here do match up, so it's just 3 over 1. Remember, that's just another example of all of these possibilities. Any combination of sine and tangent, just the coefficients. So here, as long as the things in here match up, then you're good. So here, that's why I split this up, because now I got 5x over x. That's 5, and that's 5. All right. And last one, number 40. Number 40 is just kind of a, it's this, right? Just an example of that. This is just k squared when you split up the those two, the sine squared, and that's it. All right. So yeah, there are a few hard ones in there when we got into that, like 32 to 36. No, 36 wasn't that bad. 32 and 34, I guess, were the worst ones. All right. Life goes on.